Good day, this is Team Erbium, and this is a short crash course on acid-base and donor-acceptor chemistry. In particular, we will be covering Bronsted acids and bases, acid-base properties of water, pH levels, strength of acids and bases, ionization constants of acids and bases, relationship between the ionization constants of acids and their conjugate bases, diprotic and polyprotic acids, molecular structure and strength of acids, acid-base properties of salts, oxides, and hydrides, and lastly, Lewis acid and bases. The concept of acids and bases have been defined many times in different ways. Acids and bases are existing everywhere in our daily life. Every liquid, except water, that we use have acid and basic properties. For example, vinegar, soft drinks, buttermilk, and soap. The earliest definitions were made based on their taste and their effect on other substances. Acids are those substances which have sour in taste, sharp odor, corrosive, and they turn blue litmus red. Bases are those substances which have bitter taste, odorless, slippery texture, and they turn red litmus blue. These are violent and less reactive than acids. The Arrhenius acid-base theory was proposed by Swedish Svante Arrhenius. It was first modern approach to acid-base concept. This theory is quite simple and useful. According to Arrhenius theory, acids are the compound that increases the concentration of hydrogen ions or proton in aqueous solution. The released hydrogen ion or proton is not a free-floating proton. It exists in combined state with the water molecule and forms hydronium ion. The common examples of Arrhenius acid includes hydrochloric acid, sulfuric acid, and nitric acid. Arrhenius bases are compounds that increase the concentration of hydroxide ion in aqueous solution or having at least one hydroxide ion in formula. The common examples of Arrhenius base include sodium hydroxide, potassium hydroxide, calcium hydroxide, magnesium hydroxide, and ammonium hydroxide. We have previously learned Arrhenius acid-base theory, which provided a good start towards the acid-base chemistry, but this has certain limitations and problems. After this theory, Bronsted proposed a different definition of acid-base that is based on the abilities of compound to either donate or accept the protons. And this theory is known as the Bronsted-Lowry theory, also called the proton theory of acid and base. According to Bronsted concept, an acid is considered to be a Bronsted acid which is capable to donate a proton to someone else. And a base is considered to be a Bronsted base which is capable to accept a proton from someone else. And from here, it can note that when an acid reacts with a base, the proton is transferred from one chemical species to another. In this reaction, hydrochloric acid is an acid because it is donating proton to water. Therefore, hydrochloric acid acts as a Bronsted acid, whereas water has lone pair of electrons which is used to accept the protons. Therefore, water acts as a Bronsted base. This reaction is also reversible. In the reversible case, the hydronium ion reacts with the chloride ion and again converts into water and hydrogen chloride. In this case, the hydronium ion is donating a proton called conjugate acid, and the chloride ion is accepting a proton called conjugate base. Let us have a quick review on Bronsted acids and bases. Given the question, which of the following does not constitute a conjugate acid-base pair? Is it letter A, letter B, or letter C? Keeping in mind that a conjugate acid is formed when an acid gives a proton and the base is a proton acceptor, we can say that a conjugate acid has extra hydrogen ion and a base has one less hydrogen ion. So from that, we can say that letter B does not constitute a conjugate acid-base pair. Let us now move forward with the acid-base properties of water. To start off, let us answer the question, is water an acid or a base? Well, water molecules can act as acids by dissociating into hydroxide ions and hydrogen ions. This is equivalent to, to losing a proton. Moreover, water molecules can also act as base by combining with hydrogen ions to form hydronium ions, and this is equivalent to gaining a proton. Both reactions are reversible. The hydronium ion and hydroxide ion can recombine to form water once more. This amphoteric nature means that two water molecules can even react with each other. In this case, the first loses a proton, which the second one then gains. The ability of a water to react with itself and form two ions is known as autoionization. In the autoionization of water, a proton is transferred from one water molecule to another to produce a hydronium ion and a hydroxide ion. So to answer the question, is water an acid or a base? Basically, water acts as both acid and base. Now, given the chemical equation for the autoionization of water, the equilibrium constant for the autoionization of water is Kc is equal to hydronium ion multiplied by the concentration of hydroxide ion. Because we use hydrogen ion and hydronium ion interchangeably to represent the hydrated proton and replace Kc with Kw, the equilibrium constant can also be expressed as Kw equals the molar concentration of hydrogen ion multiplied by the molar concentration of the hydroxide ion, where Kw is called the ion product constant. In pure water, it is known that at 25 degrees Celsius, the concentration of hydrogen ion and hydroxide ions are equal and found to be 1.0 times 10 raised to negative 7 molars. Thus, 1.0 times 10 raised to negative 7 molars times 1.0 times 10 raised to negative 7 molars is equal to 1.0 times 10 raised to negative 14. Whether we have pure water or an aqueous solution of dissolved species, the following relation always holds at 25 degrees Celsius. Since the ionic product of water, Kw, is a constant that links the concentration of hydroxide ions in solution to the concentration of hydrogen ions in solution, we can now say that if the concentration of hydrogen ion is greater than the concentration of hydroxide ion, the solution is neutral. If the concentration of hydrogen ion is greater than the concentration of hydroxide ion, the solution is acidic. And if the concentration of hydrogen ion is less than the concentration of hydroxide ion, the solution is said to be basic. Let us now have a quick review on the ion product of water. So given the problem, the concentration of hydrogen ions in an aqueous solution is 0.055 molars. Calculate then the concentration of hydroxide ions and determine if the solution is acidic, basic, or neutral. The concentration of hydrogen ions is given at 0.055 molars. Using the ionic product of water, Kw is equal to the concentration of hydrogen ions times the concentration of hydroxide ions. We can obtain the hydroxide concentration by dividing Kw with hydrogen ion concentration. So 1.0 times 10 raised to negative 4 divided by 0.055 molars. This will give us 1.8 times 10 raised to negative 13 molars. And since the concentration of hydrogen ion is greater than the concentration of hydroxide ions, the solution is said to be acidic. To avoid dealing with very small concentrations of hydrogen ion and hydroxide ion, in 1909, Sorensen proposed a more practical measure called pH. The pH of a solution is defined as the negative logarithm of the hydrogen ion concentration. Like the equilibrium constant, the pH of a solution is a dimensionless quantity. A pOH scale, analogous to the pH scale, can be devised using the negative logarithm of the hydroxide ion concentration of a solution. Now, consider again the ion product constant for water at 25 degrees Celsius, that is Kw is equal to the molar concentration of hydrogen ions times molar concentration of hydroxide ions, which is equal to 1.0 times 10 raised to negative 14. Taking the negative logarithm of the both sides, we can obtain negative log of the molar concentration of hydrogen ions minus the logarithm of the molar concentration of hydroxide ions is equal to 14. From the definitions of pH and pOH, we can obtain pH plus pOH is equal to 14. And this equation provides us with another way to express the relationship between the hydrogen ion concentration and the hydroxide ion concentration. Let us have a quick review on the pH levels. So given the problem, a hydrochloric acid solution contains 0.0025 molars of hydrogen ion. Calculate the pOH of the solution. Given the concentration of hydrogen ion, we can obtain its pH by taking the negative logarithm of the hydrogen ion concentration. So that this will give us negative log of 0.0025 molars. This will give us a pH value of 2.60. Keeping in mind that pH plus pOH is equal to 14, we can compute for the pOH by subtracting the pH value from 14. So 14 minus 2.60, the pOH value of this solution is 11.4.
Now let's proceed on strength of acids and bases. For strong acids, they are considered potent electrolytes, and for practical purposes, they are typically presumed to undergo complete ionization when dissolved in water. This means that they effectively break down into ions, contributing to the high conductivity of the resulting solution. Most of the strong acids are inorganic acids. Here is a list of those acids. It includes hydrochloric acid, nitric acid, and perchloric acid. And for weak acids, most acids are weak acids, which ionize to a limited extent in water. At a state of equilibrium, solutions of weak acids in water comprise a blend of acid molecules that have not undergone ionization and their respective conjugate bases. And here are the examples of weak acids. It includes the hydrofluoric acid, acetic acid, and ammonium ion. Similar to strong acids, strong bases are robust electrolytes that, for practical considerations, are assumed to undergo complete ionization when they are dissolved in water. This complete ionization implies that these strong bases effectively dissociate into ions, leading to a solution with heightened electrical conductivity. Hydroxides of alkali metals and certain alkaline earth metals are strong bases, and all alkali metal hydroxides are soluble. And here are some examples of strong bases. And take note, these metal hydroxides are not Bronsted bases because they cannot accept a proton. However, the hydroxide formed when they ionize is a Bronsted base because it can accept a proton. And for weak bases, like weak acids or weak electrolytes. Example of weak base is ammonia. It ionizes to a very limited extent in water. In this reaction, in contrast to acids, NH3 does not donate to a proton to water. Instead, NH3 acts as a base by taking a proton from water, resulting in the formation of NH4 and OH ions. So to sum up, strong acids and bases ionize completely, while weak acids and bases ionize partially. And next is the ionization constant of acids and bases. Ionization constant are equilibrium constants that describe the degree of ionization of an acid or base in water. So here are the following ionization constants: the acid ionization constant, base ionization constant, and water ionization constant. The higher ionization the higher acid ionization constant value considered as a strong acid, while lower Ka value considered as a weak acid. Similar to acid ionization constant, higher base ionization constant considered as a strong base, while lower base ionization constant considered as weak acid. In ionization of an acid in water, in this reaction monoprotic acid ionizes into hydronium ion and conjugate base A, or simply it turns into this reaction. Monoprotic acid ionizes into hydrogen ion and conjugate base A. The equilibrium expressions for this ionization is where Ka, the ionization constant for acid, at a given temperature, the strength of the monoprotic acid is measured quantitatively by the magnitude of acid ionization constant. The larger Ka, the stronger the acid. That is, the greater the concentration of hydronium ions at equilibrium due to its ionization. We need to keep in mind that only weak acids have Ka values associated with them. Here is the sample question for you to try. So which of the following weak acid is a strong? In this reaction, dissolution of solid sodium hydroxide in water to produce aqueous sodium ions and hydroxide ions, a strong base almost dissociates, so the equilibrium shifts to the left. The ionization of weak bases is treated in the same way as the ionization of weak acids. One of its examples is ammonia. When ammonia dissolves in water, it undergoes in this reaction. Equilibrium constant, it is equal to the concentration of ammonium and hydroxide over the concentration of ammonium and water. And a very few water molecules are consumed by this reaction, so we can treat H2O as a constant. Thus, we can write KBS ionization constant of base is equal to the product of equilibrium constant and concentration of water, which is also equal to the concentration of ammonium and hydroxide divided by the concentration of ammonia.
I will now report the relationship between the ionization constants of acids and their conjugate bases. When weak acids are dissolved in water, they ionize reversibly by donating a proton to water molecules. This forms their conjugate base and hydronium ions. Similarly, weak bases accept protons from water molecules, forming their conjugate acids and hydroxide ions. This process occurs through a reversible reaction, allowing for the establishment of dynamic equilibrium between the reactants and products. Now let's discuss the diprotic and polyprotic acids. Next, we will find the Kb for the conjugate base reacting as base. So when the conjugate base of a weak acid acts as base by accepting proton from water, it undergoes a reversible reaction represented as shown. Here, the conjugate base acts as base by accepting proton from water, forming its weak acid and hydroxide ions. The equilibrium constant for this reaction, denoted as Kb, is the ratio of the concentration of the products and hydroxide ions to the concentration of the reactant when the system reaches equilibrium. It is important to know that even though the reaction where conjugate base act as base might seem like the reverse of the reaction where the weak acid acts as an acid, they are indeed distinct reaction where the weak acid acts an acid and one of the product is hydronium ion, while when the conjugate base act as base, one of the product is hydroxide ions. These differences reflect the nature of the species involved in each reaction and their respective roles as either acids or bases. Now let's discuss the diprotic and polyprotic acids. Acids are substances that can donate protons in a chemical reaction depending on the number of hydrogen ions they can donate. Acids are classified into different categories. Here is an overview of the 4 categories. First is the monoprotic acid. These acids that can donate only 1 proton per molecule in an aqueous solution. Examples include hydrochloric acid, nitric acid, and acetic acid. In a chemical equation, monoprotic acids typically appear with 1 protons, and the protic acids can donate 2 protons per molecule in an aqueous solution. This means they have 2 ionizable hydrogen atoms. Examples include sulfuric acid and carbonic acid. In chemical equation, diprotic acids will typically donate 2 protons, while the polyprotic acids can donate more than 2 protons per molecule in an aqueous solution. These acids have 2 ionizable hydrogen atoms. Examples include phosphoric acid and citric acid. In chemical equation, polyprotic acids may donate 3 or more protons. Lastly is the triprotic acids, which are the subset of polyprotic acids. They are specifically acids that can donate 3 protons per molecule in an aqueous solution. Phosphoric acid is a common example of a triprotic acids in chemical equation. Triprotic acids will donate 3 protons. Diprotic and polyprotic acids show unique profiles in titration experiments, where pH versus titrant volume curve clearly shows 2 equivalence points for the acid. This is because the 2 ionizing hydrogen do not dissociate from the acid at the same time with any polyprotic acid. The first and most strongly acidic proton dissociates completely before the second most acidic proton even begins to dissociate. Let's take the example of carbonic acid, which is diprotic acid. In its first dissociation step, here 1 proton dissociates to form bicarbonate ion. This is the first equivalence point in the titration curve, corresponding to the complete dissociation of the first proton. However, carbonic acid can further dissociate. In the second step, the another proton dissociates to form carbonate ion. This is the second equivalence point in the titration curve, corresponding to the complete dissociation of the second proton. The key point here is that the dissociation of each proton occurs at different pH because the acidity of the remaining species changes with each dissociation. In this case, the polyprotic acid, like carbonic acid, the first proton dissociates completely before the second proton begins to dissociate. This is why we observe distinct step in pH versus titrant volume curve, with each step corresponding to the dissociation of different proton. The first proton to dissociate from diprotic acid is typically more strongly acidic than the second proton. This is because the presence of the first proton makes the remaining hydrogen ion less tightly bound to the molecule. In the case of sulfuric acid, the first dissociation step is as shown. This step involves the removal of the first proton from the hydrogen sulfate ion. Resulting ion is stabilized by the resonance and is still quite acidic. The second dissociation step is where the second proton is removed from the hydrogen sulfate ion, forming the sulfate ion. However, since the first proton has already been removed, the remaining sulfate ion is less acidic compared to the original sulfuric acid molecule. The dissociation constant measures the extent to which an acid dissociates in a solution. A larger Ka value indicates a stronger acid, while a smaller Ka value indicates a weaker acid. For sulfuric acid, Ka is large because the first dissociation step occurs almost completely in solution, producing a high concentration of hydrogen ion, while the second dissociation constant is smaller because the second dissociation step is less favorable. Even though some hydrogen sulfate ions dissociate to form hydrogen ions and sulfate ions, the extent of the dissociation is much lower compared to the first step. Similar to the diprotic acid, in polyprotic acids, the first proton to dissociate is typically the most strongly acidic, followed by the second, then the third. This is because the presence of each subsequent proton changes the chemical environment and the influences of the acidity of the remaining proton. For example, is the phosphoric acid. The first dissociation step is where the first proton is removed from the phosphoric acid to form dihydrogen phosphate ion. This step usually occurs almost completely, resulting in a high concentration of hydrogen ion in solution. And the second dissociation step is where the second proton is removed from the dihydrogen phosphate ion to form hydrogen phosphate ion. However, this step is less favorable compared to the first step, resulting in a smaller dissociation constant. The third step is the third proton is removed from the hydrogen phosphate ion to form phosphate ion. This step is even less favorable than the second step, resulting in the smallest dissociation constant. As the diprotic acid, the dissociation constant for each step measured the extent to which the acid dissociates in solution. In this case, the phosphoric acid, the first dissociation constant is large because the first dissociation step occurs almost completely, leading to a high concentration of hydrogen ions in solution, while the second dissociation constant is smaller than the Ka1 because the second dissociation step is less favorable, and the third dissociation constant is the smallest because the third dissociation constant in step is the least favorable of all, resulting in a lower concentration of the hydrogen ions in solution compared to the first and second steps. For some key takeaways, here is the summarization of the report. Well, the polyprotic acids overview. The polyprotic acids are acids that can donate 2 or more acidic protons in solution. And diprotic acids can donate 2 protons, while triprotic acids can donate 3. Equivalence points in titration. Polyprotic acids exhibit as many equivalence points in titration curves as the number of the acidic protons they can lose. For example, a diprotic acid would know 2 equivalence points and triprotic acid would show 3. While the order of dissociation constant in polyprotic acids, the first dissociation constant is always the largest, followed by the second, and so on. This trend indicates that the protons become progressively less acidic as they are lost from the acid molecule. And lastly, the existence of ionic species, even though the tendency to lose each acidic proton decreases as subsequent one are lost. All possible ionic species do not exist in solution for polyprotic acid. To calculate their fractional concentration, one can use equation based on the equilibrium constants and the concentration of protons in solutions. Next, I will discuss the molecular structure and strengths of acids. Carboxylic acids are significant subgroup of organic oxoacid, distinguished by the presence of one or more carboxyl group. The general formula of carboxylic acid is RCOOH, where R represents a monovalent functional group. These acids are prevalent in nature and are vital in numerous biological process and industrial application. For example, is the formic acid found in ants and acetic acid responsible for vinegar sour taste are among the simplest examples. Carboxylic acids can have multiple carboxyl groups, making them dicarboxylic, tricarboxylic, and so forth. Oxalic acid, composed of two connected carboxyl, is the simplest dicarboxylic acid, while the malitic acid, featuring six carboxyl groups, is an example of hexacarboxylic acid. While salts and esters derived from carboxylic acids are referred to as carboxylates. When a carboxyl group loses a proton, it forms its conjugate base known as carboxylate anion. Carboxylate ions exhibit resonance stabilization, meaning that the negative charge can be delocalized over multiple atoms within the molecule. This is increased stability compared to the corresponding carboxylic acid contributes to the enhanced acidity of carboxylic acid relative to the alcohols. Binary acids are molecular compounds composed of hydrogen combined with a second nonmetallic element. Example includes hydrofluoric acid, hydrochloric acid, hydrobromic acid, and hydroiodic acid. Among the binary acid listed, hydrochloric acid, hydrobromic acid, and hydroiodic acids are all classified as strong acids, while hydrofluoric acid is considered a weak acid. Acid strength is typically measured by the pKa value, where a lower pKa values indicate stronger acids. So this is the hydrochloric acid, which is a clear colorless solution of hydrogen chloride in water. It is highly corrosive, strong mineral acid with many industrial use. Hydrochloric acid is found naturally in gastric acid. It is a member of the binary acid. So chlorine is larger and has more electrons, and therefore the HCl bond is longer and weaker. In the presence of water, the electrostatic attraction between water's partially negative oxygen and the partially positive hydrogen on HCl is strong enough to break the HCl bond, and the ions dissociate in the solution. So let's answer why hydrofluoric acid a weak acid. The fluoride ion produced when hydrofluoric dissociate is relatively small and highly electronegative. This makes it highly stable and less inclined to accept proton, which further reduces the tendency of hydrofluoric acid to donate protons and makes it a weaker acid compared to the other hydroholic acid. Overall, the combination of strong hydrofluoric bond and the presence of hydrogen bonding and the stability of the fluoride ion and the solubility effects collectively contribute to the making of hydrofluoric acid a weaker acid compared to the hydrochloric acid, hydrobromic acid, and hydroiodic acid.
Now let us discuss the acid-base properties of salts, oxides, and hydrides. Salts, being strong electrolytes, dissociate completely in aqueous solution to produce the ions which they are composed of. Therefore, salt solutions can be acidic, basic, or neutral. Salts are formed when acids react with bases, which results in the neutralization of their acidic and basic properties. When a strong acid reacts with a strong base, the resulting salt will be neutral. For example, the reaction between hydrochloric acid and sodium hydroxide will result in sodium chloride, which is a neutral salt. If a weak acid reacts with a strong base, the resulting salt may exhibit basic properties. For example, the reaction between acetic acid and sodium hydroxide forms sodium acetate, and in the solution, the acetate ion can accept protons, acting as a weak base and increasing the pH of the solution. Conversely, when a strong acid reacts with a weak base, the resulting salt may exhibit acidic properties. For example, the reaction between hydrochloric acid and ammonia forms ammonium chloride. In the solution, the ammonium ion can donate protons, acting as a weak acid and thereby decreasing the pH of the solution. If both the acid and the base are weak, the resulting salt's acid-base properties depend on the relative strengths of the acid and the base. The pH of the solution will be determined by the ionization of both the acidic and basic components of the salt. In this case, the salt would be acidic if the Ka of the acid is greater than the Kb of the base, and it will be basic if the Kb of the base is greater than the Ka of the acid. And the salt will be neutral if the Ka of the acid is equal to the Kb of the base. Oxides are compounds composed of oxygen and another element. They can exhibit acidic, basic, or amphoteric properties depending on the nature of the other element. When it comes to acidic oxides, it reacts with water to form acidic solutions. These oxides typically contain nonmetals and react with water to produce oxyacids. For example, carbon dioxide dissolves in water to form carbonic acid. Sulfur dioxide dissolves in water also to form sulfuric acid. Other examples of acidic oxides are sulfur dioxide, and when it dissolves in water, it forms sulfurous acid. And the next example is nitrogen dioxide, which when it reacts with water, it forms nitric acid. And the phosphorus pentoxide, when combined with water, it produces phosphoric acid. Basic oxides react with water to form basic solutions. These oxides contain metals and react with water to produce metal hydroxides. Oxides of group 1 and 2 are basic except for beryllium oxide. For example, calcium oxide reacts with water to form calcium hydroxide. And sodium oxide reacts with water to form sodium hydroxide. Both of these dissociate in solution to form hydroxide ions, which is why they make the solutions basic. Some more examples of basic oxides are magnesium oxide, which reacts with water to form magnesium hydroxide, and barium oxide, which combines with water to produce barium hydroxide. The basic oxides also react with acids. This reaction will form salts and water, and it is a type of neutralization reaction. Here is the general equation for the reaction between a basic oxide and an acid. For example, this reaction produces calcium chloride and water. Similarly, when sodium oxide reacts with sulfuric acid, the reaction produces sodium sulfate and water. Acidic oxides also react with bases. It also forms salt and water in a neutralization reaction. And here is the general equation for the reaction between an acidic oxide and a base. In this equation, X represents a nonmetal or metalloid element, and Y represents the number of oxygen atoms in the acidic oxide molecule. For example, when sulfur dioxide, an acidic oxide, reacts with sodium hydroxide, the following reaction occurs. This reaction produces sodium sulfite and water. Similarly, when carbon dioxide reacts with calcium hydroxide, the reaction proceeds as follows. This reaction yields calcium carbonate, also known as limestone, and water. Amphoteric oxides can also behave as both acids and bases depending on the conditions. They can react with both acids and bases to form salts. For instance, aluminum oxide can react with both acids and bases. With acids, such as hydrochloric acid, it forms aluminum chloride and water. With bases, such as sodium hydroxide, it forms sodium aluminate and water. In these reactions, aluminum oxide behaves as an acidic oxide when reacting with bases and as a basic oxide when reacting with acids. Basic hydroxides are compounds that contain the hydroxide ion and exhibit basic properties when dissolved in water. These compounds are often formed by the reaction of a metal with water or a metal oxide with water. Here are some examples of basic hydroxides. Sodium hydroxide, also known as caustic soda, is a strong base. When dissolved in water, sodium hydroxide dissociates completely into sodium ions and hydroxide ions. Calcium hydroxide, which is also known as slaked lime, is a sparingly soluble base. When it dissolves in water, calcium hydroxide dissociates into calcium ions and hydroxide ions. Potassium hydroxide is another strong base that is commonly used in industrial and laboratory settings. And similarly, when dissolved in water, it dissociates into potassium ions and hydroxide ions. These are just few examples of basic hydroxides, and various other metal hydroxides such as magnesium hydroxide and barium hydroxide and many others also exhibit basic properties when dissolved in water. Now let's explore the acidity of hydrides, which are compounds composed of two atoms, one of which is a hydrogen atom. In general, the acidity of hydrides increases from left to right across the periodic table and also increases as we move down a group. This trend signifies that the acidity of hydrides is influenced by the electronegativity and size of the elements involved. As we move from left to right across a period, the electronegativity of the elements increases, leading to a greater tendency for the hydrogen atom in the hydride to ionize and release a proton. Metal hydrides are typically basic or neutral. For example, sodium hydride and lithium hydride are both basic due to the strong basicity of the hydroxide ion released upon dissociation. Strong acids such as hydrogen chloride and hydrogen bromide are found on the rightmost and bottommost region of the periodic table, and these are strong acids. Hydrofluoric acid, positioned at the top, is a weak acid due to its relatively lower electronegativity and weaker hydrogen bonding. Hydrogen sulfide and hydrogen selenide are weak acids since we moved back a group and the acid strength decreases. Moving one more group, we get weak bases. And when we move one more group backwards, we get neutral compounds. Now, let us discuss the Lewis acids and bases. Lewis acids and bases are a broader classification of chemical species compared to Bronsted-Lowry acids and bases. Lewis acid is defined as any chemical species that can accept a pair of electrons to form a coordinate covalent bond. The Lewis theory of acid-base reactions describes Lewis acids as electron pair acceptors and Lewis bases as electron pair donors. In this framework, a Lewis base can donate a pair of electrons to a Lewis acid, which will result in the formation of a coordinate covalent bond between them. This product, known as a Lewis adduct, is formed through the sharing of electrons between a Lewis acid and a Lewis base. As electron-rich entities capable of donating electron pairs, Lewis bases are commonly classified as nucleophiles, and conversely, Lewis acids as electron pair acceptors can be categorized as electrophiles since they behave as electron pair acceptors. Lewis acids and bases are named after the American chemist Gilbert Newton Lewis, who made invaluable contributions not only in the development of the concept of Lewis acids and bases, but also in the fields of thermodynamics and photochemistry. And the reactions involving the H plus ion typically occur in acidic solutions and are central to various chemical processes, including acid-base reactions and protonation reactions. In acid-base reactions, H plus ions act as the acidic species that donates protons to bases to form water or other products. For example, in this reaction, hydrochloric acid donates a proton, forming the ammonium ion and the chloride ion. H plus ions can also protonate various functional groups or molecules, which results in the addition of a proton to the molecule. For instance, here, the H plus ion protonates water to form the hydronium ion, which is commonly found in acidic solutions. This is Team Erbium, and this concludes our discussion for CRTV topic 011 in inorganic chemistry.